They're like, she had the strawberry hat from Shaken and the Strawberry. She was so cute.
That'll be interesting. It really bothers me how like their editors are all like, this is such a thing with all the sex you, Amelia, and blah, blah, blah. Like, that's her brother. Like, do not. She's like, I am in a worse position than you. I'm like, no, you're not. And Meredith was there for all of it. And like, did you tell Amelia, or like Addison? Yeah. I haven't heard that Addison for episode for season. Yeah, because she was like private practice. Yeah. So I feel like she's really cool. Call her back. Yeah. Your ex-husband died. Right. Like, you might want to know. That part where Alistair and Amelia was like, I asking her to tell her all the I was like, going on. Yeah. Oh my God, what's going to happen? What's going to happen? Yeah, I was like, if I was funny, I'd be like, yeah. So annoying. I can't believe that happened. I was wondering why everyone was so, like, she killed all of us. Oh my God. I was like, kind of certain, like, you know, she's like, you need to calm down. I thought something was going through her mouth the entire time, but you said that. Okay, I was like, oh my God. Yeah, he's on her mouth. Yeah. Okay. Yeah, I know. Yeah. Might as well. I wonder what's going to happen. Yeah. I hate that how this was like getting all angry at Alex when I was trying to tell her. I was like,
Okay, we've got 12:30. Why don't we get started? Good afternoon, S&P. All right. Well, welcome to the end of week number 9. Who's ready for a weekend? All right. We're almost there. I can't believe, as I said to my earlier class, we're going to be in double-digit weeks when we come back on Monday. We're also going to be starting audition, the sense of hearing. So this will be our last day to spend some time on the visual sense. And I hope to make a couple of connections today. First, we want to link back in time to our study of attention, and we talked a little bit about attention and the physiology of it on Monday, and we're going to see how that plays an important role in learning. And on the topic of learning, I wanted to not only set up today's paper, where we discuss learning directly, but also harken back to an interesting story by Oliver Sacks. And thank you all for, many of you came out to the Oliver Sacks presentation last night. Oliver Sacks told a wonderful story about a fellow that he called Virgil, who had been blind all his life, or almost all of his life, and very, very late in life, he had his vision restored, but he couldn't really see in any meaningful way. Everything was connected, but he hadn't learned to see. So perceptual learning is actually a very, very important topic, because we do have to learn how to see. So we'll set the stage for that, and we'll get into this article in great depth. But to do that, I did want to see if somebody could just give us a few reminders about what we learned on Monday about attention and its physiology. So that was the MIT paper. Can anybody just give us a couple of the highlights from that paper and that discussion? We had search tasks and pop-out tasks, to remind you. We did a demo, too, about clapping our hands, however that went. Okay, is that a hand or is it? Okay, thanks, Alex.
It kind of covered top-down processing versus bottom-up,
okay.
And how they, depending on the task, or I guess whether it's grabbing your attention or it's something your extended consciousness is doing. I think we kind of touched on that. Dictates kind of where the signal starts and where it ends.
Okay, right. So we get different patterns of signals starting and signals ending depending on the type of attention, right? And we might think of search as being a relatively top-down type of attention. We might think of that as, some people will call that endogenous attention. And it's kind of related to this idea of extended consciousness. That's a really good connection. Okay, and then every once in a while somebody yells, hey, in the classroom, and that grabs our attention. We might call that exogenous attention, and that has a different pattern. It has a different frequency at which the neural synchrony is operating. and it has a different start and end location across the different cortical lobes. Okay, so we're going to need attention in this paper, as you might recall, as you did your TED Ed responses. To help set us up, I'm going to play a few minutes, most of a video that a couple of students made a little while back. You might recognize some of these students, you might not recognize some of these students, but I think it sets the stage very nicely for today's conversation. Okay, so let's go to here. Okay, Alex, I wonder if we can turn down, why don't we turn both of those down?
Okay, so our presentation today is going to be on simultaneity. So Bryn and I said the word simultaneity at the same time. That is an example of simultaneity, is when two different things occur at the same time. Another example of auditory simultaneity would be if Bryn and I were talking at the same time versus different times. So how does that whole idea of simultaneity transfer to our visual system? Well, visual simultaneity would be making the distinction between visual cues that are happening at the same time versus different times. So have you ever wondered how exactly our brain makes that distinction between things that happen at the same time versus different times? And that's what our presentation is going to look at. So how exactly do we study simultaneity? The most common method is called signal detection theory, and it basically just looks at the responses of participants in a simultaneity task as to whether they have the correct response or the incorrect response. So for a correct response, there are two different types. The first would be if a cue is simultaneous, and the participant reported that it was indeed simultaneous. That would be a hit. But if the visual cues are not simultaneous, and they reported that they were not simultaneous, then that would be a correct rejection.
There are also incorrect responses. For example, if a visual stimuli, if they were not simultaneous, and the participant reported that they were, that would be a false alarm. On the other hand, if the stimuli were simultaneous and the participant failed to report so and instead reported that they were not simultaneous, that would be considered a miss.
Did you know that?
Viewers, and seeing the difference between things happening at the same time versus things happening at different times when they happen in our right visual field, over there where Rachel is standing, compared to our left visual field.
Now you know. So we kind of wanted to do a visual demonstration of what exactly that concept is. So, for example, if you are a participant and you're looking at the fixation point on the screen, and you would have to make the distinction between whether Bryn and I are blinking at the same time or different times. So if you were trying to make that judgment, if the blinking were happening at the same time on the right visual field, like I was blinking, then you would be worse at telling if that was simultaneous or not, versus if Bryn was blinking at the same or different time. And so we kind of wanted to look at why exactly does this poor acuity in the right visual field happen and not in the left visual field. Research has found two different explanations for that. The first one being that if there are distractors in someone's visual view, then that could account for the poor acuity in the right visual field. So if Bryn was being a distractor and I was asking you to focus on the fixation point and whether over here this is happening at the same or different times, but Bryn was distracting you, that could account for why the right visual field is not as good at telling that judgment than the left visual field. The other explanation is best described through an example. So if Bryn and I wanted to go to the mall, and there's a bus that left every hour at 2 o'clock. If we wanted to catch that 2 o'clock bus, and Bryn arrived at 1:20 and I arrived at 1:45, then we would get to the bus stop at different times, but still both make the 2 o'clock bus and both get to the mall at the same time. But if Bryn and I arrived at those two different times for a bus that left every half hour, then he would be on one bus and I would be on a different bus. And then we would get them all at different times. So we can think of that example in terms of our visual system. And then if two different visual cues arrive at different times, then the left visual field would be like the bus that left every half hour, and then it would be able to better distinguish between stimuli arriving at different times or the same time. Whereas the right visual field would be equivalent to the bus that leaves every hour, where it would be more difficult to tell whether stimuli are arriving at the same or different times.
We're also looking to explore when this right visual field.
I'm going to pause this for a moment. This is going to be critical to understanding graph numbers 2 and 3 in our paper. Okay, so they're going to set something up here between a guitar, its amplifier, and the connection between them. So here comes Bryn.
That's it first. In other words, where in our visual pathway, where is responsible for why we are worse in our right visual field compared to our left visual field? And a nice way to think about that is comparing our visual system to a guitar that is hooked up to an amplifier through a cord. And in this example, the guitar is like our retina. The cord connecting the guitar to the amplifier are the nerves running from our retina back into our brain. And the amplifier is our visual cortex. So if you're playing the guitar and no sound is coming out, and you think, well, there's either something wrong with the guitar itself, there might be something wrong with the connection between the guitar and the amplifier, or perhaps the amplifier isn't working. The same thing with our visual system. Is this deficit from something with the retina, something with the cortex, or something between the retina and the cortex? To study this, researchers had participants do a pre-training test.
Okay, so they're starting to get into some of the details of the study. I wonder, Alex, if we could turn those lights all the way back up on. So thank you very much. So they set the stage, I think, quite nicely for our conversation about this paper. Let's go back to that. Okay, the right hemifield deficits in judging simultaneity. This was published with 2 Denison students. Probably none of you know Jenna Kelly, who's now in her last year at NYU's neuroscience program. She's doing really interesting work in trying to understand circuitry within the visual cortex. There are 6 different layers, and she's doing lots of recordings trying to figure out how layer 3 connects with layer 5 and stuff like that. Michael Vaughter is a more recent graduate, the class of 2014. How many people know Michael? I think we had some indicators last time, so probably some of our seniors would know Michael anyway. And Michael is now at Seton Hill University, I think pursuing an MBA. Okay, so we did this research together, and I would like to start getting back to you with some TED Ed questions. So I wonder if in your own words we can summarize the study's purpose and maybe some of the main findings. Bryn and Rachel gave us some indication about large topics that are addressed in this article. So why don't we turn it over to you? This is your response to number 1. Okay, thank you, Claire.
The main purpose of the study was to find out when and why the right visual field is has latencies or is efficient in seeing simultaneity between flashes.
Yeah, okay, right. So why is it that things in our right visual field are not perceived as precisely in time as in our left visual field? And we're trying to understand what's causing that, and maybe where in the visual pathway might we be able to discern that. What I think is kind of interesting about this, it's an entirely behavioral paper, but it's the kind of paper that would fall in what we might call behavioral brain research. There's in fact a journal called Behavioral Brain Research, and on Thursday and Friday of next week we're going to have a visitor, Dr. Stephen Mayer, who publishes frequently in those kinds of journals. We try to draw an inference about the nervous system by looking purely at behavior, and some inferences can be drawn. So first, I just wanted to emphasize, I think it is a little bit peculiar that, and if you'll excuse my back, that if things are happening quite quickly across the front of the room, and you're fixating here on the screen, you'll have greater precision in time for what's going on that side than on that side. At least on average, that's true. And it's peculiar because as we look out through a typical scene or to a typical scene, we're not aware that there's any difference in timing. Right? It all seems to be happening in a very smooth manner. But if you make very precise psychophysical measurements, you can show that we actually are faster in our left visual field than we are in our right visual field. So that's about the level of detail that we want. Thank you, Claire. Okay. Anybody want to tell us how we might operationally define hits and false alarms? Bryn and Rachel did a little bit of that, but maybe we can just get a reminder. Hits and false alarms from signal detection theory. Okay, why don't we go with Zach?
So recognizing temporal asynchrony would be when it did actually occur would be a hit.
Okay.
And then a false alarm would be saying it did occur when it didn't actually occur.
Okay, right. Okay, so we're almost looking for an asynchrony, right? That's the signal that we're trying to detect, right? That's the smoke that we're trying to detect. And if it's actually there and we pull the alarm, then we'd have a hit. But if it isn't there and we pull the alarm, then we have a false alarm, and we can go from there. Okay, so that's pretty nicely described. Okay, then we get into just a little bit of the details about why it might be the case that one hemifield performs differently than another, and we generated at least 3 hypotheses. There could be other hypotheses as well, but those are schematized over here. And one is the neural noise hypothesis, and I'll keep just the front row down so we don't put you to sleep, and we also get some nice contrast up here. The neural noise hypothesis, the low temporal acuity hypothesis, and the excessive spatial integration hypothesis. Okay? Can somebody maybe help us out in trying to understand this portion of the diagram? Even if you can't go all the way, Liz will give it a try.
So my answer was that the hypothesis is that the right visual field necessitates arising from neural noise with increased right visual field misses and false alarms.
Okay. It's going to do that, all right? It's going to give us, so both kinds of errors, and I think Bryn described that there would be 2 different kinds of error types in the video, right? And we've known about these 2 different kinds of error types since about the first week of class. We can have false alarms or we could have misses, and those are going to be generated in either case. So here on this diagram, we have space going this way, and we have time going this way. We can think of this as being earlier in time, and this as being later in time. Okay? So what could happen is it might be something like this. 2 events happen at the same time. These 2 hands hit this podium at the same time. Okay? And if I can separate them a little further, they could land at the same time. I could put them both into one visual field. I can put them both into the other visual field, and so forth. It could be the case that we have some noise, which is to say some variability, in the timing of our neural responses. Okay? So it might be the case, for example, that one neuron that's tuned to this region of space and another neuron that's tuned to this region of space are more or less synchronized. Okay? Their firing is more or less synchronized. It could also be, though, that this one just had an action potential and is now in its refractory period. Does anybody remember hearing about refractory periods in Intro to Psych? Can somebody just give us a little overview of what that means, the refractory period? We'll go with some of our neuro folks. Melanie.
So basically, like refractory period, once a neuron fires, there's this period where, regardless of what kind of stimulation that neuron is getting, it cannot fire again. Okay, right. Is that what you were going to add, Alexa? Okay. So how many people are okay with that? Does that sound okay? So the neuron is momentarily down. So what could happen is that something occurs out here in the real world at a particular instant when a neuron or a group of neurons might be in their down phase. Okay? And maybe that visual stimulus lasts for a little bit longer so that now as that neuron comes back online, it can report that something happened. But maybe one of the neurons was a little bit over here, the other one is a little bit over here. They're a little bit out of sync, and one of them can jump and act on it right away. The other one has to wait a little bit. Okay? People okay with that because of these refractory periods? So something physically happens simultaneously out here, but the neurons are now going to be mismeasuring them just a little bit. One might be relatively ahead, one might be relatively behind. Okay? So that's kind of interesting. We could generate a mismatch in reporting to the cortex, right, just because there's a little bit of slop in where these neurons are relative to each other. When I say slop, I'm talking about variability in their timing that might arise from something like these refractory periods. And we call that variability noise. Is that okay? So something was actually simultaneous, but maybe it's perceived as not being simultaneous. Here's another one. Suppose this one occurs first, this one occurs second, but even though this one occurred first, the neuron that's picking it up was in a refractory period. So now, even though it occurred first, it gets reported in a little bit of a delayed manner. Okay? So now it looks like, to you and me, these 2 happened at the same time, even though out here in the real world, they were asynchronous in time. This one came first. Okay? So we could either get more misses or more false alarms because this thing is sliding around. And if there's more slippage left and right for neurons that are tuned to this hemifield than for neurons that are tuned to this hemifield, then we'd have more errors over here than we would have over here, and we'd have a left visual field advantage, a right hemifield deficit. Who's following that? Is that working for us? Okay, so that's one of the ways this could go. Okay? We'll call that the neural noise hypothesis. Okay, then we have this other one, low temporal acuity. Anybody want to? Okay, Jess has something on that one.
That you would experience an increase in right visual field misses compared to left visual field, like no difference
Okay, right. So now what you might notice is that we're at the same height, so we haven't changed anything on the space domain. We're going up the same level in height, same level in space, but now we have a much broader temporal interval that we're averaging over. And that's going to generate cases in which there might be two things happening out here in the real world that are actually different in time. Okay? But this tends to average things together in time over a relatively long interval, at least in comparison to this one. It's averaging over a smaller interval. Okay? One way of thinking about that was the point that Rachel was making in the video. Maybe to pick up on the bus thingy. Can we do that again? Help us out in understanding how the bus diagram or the bus example might relate to this. Talked about two different kinds of buses. One left at 2 o'clock, right? When did the other one go? Okay, so one's running hourly, and one's running on the half hour. Okay? So it could be the case that Bryn arrives at, was it 1:20, and Rachel arrives at 1:45. Those are distinct in time. Okay? And if you have sufficiently precise measurement in time, you can distinguish those from each other. But if you're averaging over a much, much longer interval, right, those two would get blended together in time. And if you were standing at the mall where this bus is arriving, you would never know that Bryn had arrived at an earlier time than Rachel had. It would have been integrated over. So we might have just lower temporal acuity. We might be averaging over larger units of time in the right hemisphere, right hemifield, versus the left hemifield. Is that okay? Is that working for us? Yeah. Okay. All right, this one's a little bit different. Okay, now we can see something is going on in space, and I wonder if somebody can help us out with this. Excessive spatial integration. Sarah's got something.
It's like almost the opposite of the low temporal because you have an increase in the false alarms and you're changing.
Okay, very good. Thank you for that. Okay, so now what's going to happen is, and that was a really good observation, that it's really the same idea, but now the extension is in space rather than in time. Okay, so what could happen is that maybe I've got something like this. Two stimuli come on simultaneously in your right visual field. There they are, they're on, okay? But what also happens is something comes on at a different time over here. This shouldn't matter. This is an irrelevant stimulus on this particular case. These are the discriminanda. This is what will get you the correct response or not. So these two are simultaneous. Something asynchronously happens over here. But if your brain inappropriately averages over the whole region of space, now you can say that, well, yeah, these two came on at one time, but this one came on asynchronously, so there's some asynchrony out there in this huge region of space. Those must have been different. So now you report different, even though these two came on at the same time, because you're being fooled into thinking there was a difference by this spatially irrelevant distractor. Who's okay with that? That work? Okay. So these are at least three different ways that we could generate errors, and they might be more pronounced on this side, your right visual field, than on your left visual field. And we're going to try to figure out which of those best describes the nature of the deficits that we have on the right side, or the advantage, if you like to think of it positively, on the left side. Okay? So it's pretty cool that we can just look at behavior and maybe try to understand what's going on in the visual pathway to generate this asymmetry that we have in our two hemifields. Questions about any of that? Right? Sometimes a picture will say 1,000 words for us. Okay. Now we get to this thing. I think that's the next question. Why don't we just go with this one? I think that would have been one of the next questions. Can somebody help us out in trying to understand Figure 2A, and then we'll make our way to Figure 2B. But what's cooking over here? Something about transfer of training. Okay, thanks, Zach.
In 2A, a single stimulus-driven neuron ensemble is it's connected to two different tasks.
Okay.
And then in B, there are two stimulus ensembles connecting to a single task.
Okay. All right. So thank you for doing that. We can think of this as being, fortunately, it's on the bottom of the picture. It's also like the bottom-up portion of our visual system. This is very early in the visual pathway, if you will, something like the retina. And then you can think of this as being connections going out of the retina, maybe to two portions of your brain that are going to perform different kinds of tasks on the same retinal information. Okay? Alternatively, we can have a single task that's being performed on two very different portions of the retina, or two very different physical stimuli, whatever those might be. They can be different areas of the retina or something else. Okay? How many people are following that? Yeah? Okay. Is that a question? Please.
Yeah, can you go through B just one more time?
Yeah, I can. In fact, I'll go through both of them. I did want to just connect to the video, okay, in a couple of different ways. First, I think it was Bryn was telling us about a guitar. Okay, could somebody help us out in relating Bryn's example about the guitar to what's going on in either of these diagrams? Okay, thanks.
In figure 8, the larger bottom oval is going to be the guitar.
Okay.
And then 2 separate arrows.
Yeah, in this case, we have 2 chords, so it's a little bit different from what you were describing, okay? And then these ovals up top are, what are those? Those are the amplifiers. Who's okay with all of that, okay? So this is happening relatively later, right, in the visual pathway. This is happening relatively earlier in the visual pathway, so more akin to the guitar and more akin to what's amplifying the guitar, and we have some connections between those two, okay? Same thing over here, right? Now it's almost as if we have 2 guitars that are separately feeding into one given amplifier, okay? So that's that idea. Who's all right with that much? And we do have a question from Tawny. Thank you.
So would that mean like the figure 8 and 2A would be like 2 different amplifiers?
Yeah, we have 2 different amplifiers, okay? And I'm going to see if I can say just a little bit more about that, Tony. But you're exactly right. We have 2 amplifiers here, and we have 1 guitar, okay? Okay, back to Intro to Psych. How many people remember doing something called the Stroupe test? I know that there are some people in the room, okay? Who can tell us what the Stroupe test was all about? Can I put you on? Okay, thank you, Gabby.
So it's like a very attentional demanding task.
Okay.
You have to say the color of a word that's written. It's usually the name of a color, but it could be congruent, which is like the word red in red ink, or it could be the word blue in red ink.
Okay.
It could be non-congruent.
Okay. Mm-hmm.
So you have to say the name of the color instead of just trying to read the word, which is like what's programmed in our mind to do. Yeah,
right. Okay, and maybe in a jiffy I can call up some Stroupe. Stroupe is so famous, I'm sure I can get a couple of Stroupe stimuli. Lickety-split. Hope I can. Okay, so that's the idea, right? And you can see, here we have something that is congruent, okay? So we have now sensory information that this is written in green ink, if you will, and red ink and blue ink, and it's also spelling that word out, okay? So these are all congruent up here, and here we have an incongruence. Is that working for us, right? So here the word blue is spelled in red ink, and so forth. So this is one of the challenges. Now, what you can do is let's just take this set for a moment, okay? I can present to you this set and this set only. Okay, so this is the incongruent set. And what I could ask you to do is just read the semantic representation of the word. So what does this word spell? What do these letters spell? And that's the word blue, purple, red, green, purple, and green, right? Okay, that's the word that we're spelling. And then I can ask you, as Gabby mentioned a moment ago, to forget what it's saying semantically and tell me what it's saying in a sensory manner. So there's the sensory task and there's the semantic task, all operating on the same set of stimuli in this particular case. Who's okay with that? Is that working? That's what's cooking over here. Okay? I can give you these incongruent stimuli, and sometimes I say, just read the letters of the word and tell me what they spell out. What's the semantic representation, or what's the sensory representation? Okay? And that's where the challenge comes. But in one particular case here, we have 1 stimulus and now 2 different tasks. Is that working for us? Yeah? Okay. Here's something else I think I can maybe refresh your memory with. Maybe we can do something like this. Who remembers doing color demos where we did color adaptation? You had to stare at a fixation crossing. We had these geometric shapes that were differently colored. People remember that? Yeah? Okay. So you stared there for a while, right? And then what happened? How did that... Thanks, Maggie.
We stayed at the fixation point and kind of took note of the colored
Okay.
shape, and then we changed it to the same fixation point with blank kind of shapes, and we still got some pigmentation.
You got a color after effect, right? When we took the chromaticity away physically, you had psychologically a color after effect. Okay, all right. So that's pretty good. Then what? Anything else happened in that? That's exactly right. What else happened in that demo? Yeah.
We moved the fixation point.
Okay, so we moved the fixation point. Yeah. Okay. So all we have to do is ask one question: what color are you experiencing? And when you're fixating here after having adapted, you experience some light pastels, right? When we turn the stimuli white, you experience some very light pastel colors. And then we moved your eyes up here, they turned white, and then back there were pastels again, all the way down and back up. We're asking only one question. What color do you experience psychologically? But we're changing the retinal information by having you look up, back down to the center, all the way down, back to the center. Who's okay with that? Okay? So we can have one task while manipulating the retinal stimulation, or we can have a constant retinal stimulation while manipulating the task. Yeah? Is that all right? Okay. All right. Huh. What's the deal here? Anybody want to help us out with this one? Maybe we need to take an interim step. Does anybody want to help us out with a limiting agent? Okay, we'll go back to this one. Okay. Think about something called the limiting agent or the limiting reagent. We had a TED Ed question on that. Okay, thanks, Meg.
Well, the limiting reagent is the substance that's completely taken over by kind of the whole, like everything else. So once it's completely gone, it limits that kind of reaction. Like that reaction stops with it unless you put more of that substance in. So I guess what figure 3 is showing is that showing how like perceptual, like the perceptual learning, is kind of like the limit of how it affects your judgment.
Okay, yeah, really good. That's the idea. We're trying to take this idea of a limiting agent and link it to this notion of learning. Okay? So if I ask you to make some judgments about things that are happening in time out here in the real world, you can do it with some level of precision. And we already know that you can do it better generally on your left side than you can on your right side. Okay? So then we can begin to ask, gee, where is the problem on the right side arising? Is the problem arising relatively early at the guitar level or the sensory level? Is it in the connection between the guitar and the amp? Or is it happening a bit later at the level of the amp, akin to the later levels in the visual pathway, maybe the visual cortex, maybe beyond that? Okay, so we're trying to figure out where's the breakdown in the right-hand side? Is it coming from here, here, or here? Is that working for us? Yeah? Okay. So let's dial back just for a moment. And what we can do is we can train people on a particular task, and let's just say that the limiting factor had been right about here. Okay? If it were the case that that were the limiting factor, and we could train people, and we got an improvement here, and the sensory response got to be more and more and more precise, then everything downstream from that would benefit. Okay? We'd be able to send a better signal this way, and we'd be able to send a better signal that way. Who's okay with that? Okay? Because this was setting the limit, right? This was the limiting factor. It could have been the case, though, that the limiting factor was maybe here or over here, right? So the limit could be set much later in the sequence. And if that were the case, let's say that it's at the task level that we're setting the limit. There's something relatively late in the visual pathway that's setting the limit on your performance. Then, if I can clean that up by practice, it wouldn't matter whether the new information was coming from this side or that side. This had been setting the limit. I should get some kind of generalization, even to other kinds of stimuli. Who's following that? Is that working for us? Okay. So we're trying to lay out where's the limiting factor. At what point in the visual pathway are we finding some kind of a limit? Yeah. Okay. All right. Why don't we go ahead? I think we've laid the groundwork now enough. We'll just see if we can have somebody walk us through. We'll skip over that one. I want to get to a stimulus picture if I can find it. We'll have somebody tell us about the judgment that we're making. Here they are. And maybe I can make that nice and big. Okay. Somebody want to walk us through what the task was? Actually, we had two tasks here. I can't tell if that's too obvious or too not so obvious, but is that a hand, Alex, or it's okay if it wasn't?
So for some oral tasks, they had two peripheral stimuli shown.
Okay.
And you had to say same or different as far as timing.
As far as timing goes, right? Okay.
Yeah.
So you have to. So here's your fixation, and you're going to fixate here and attend here. Okay. These guys go away. Okay.
And then for spatial, you're looking at the peripheral cues and saying if they're the same or different forms.
Right. So in either case, we're going to be making a same or different judgment. We also ask you to pick up a letter. Is it clear to you what letter that is? It might be. We tried to make it really faint. There's a letter N appearing there, so that we've got you focusing really intensely, and then we can flash these just for 100 milliseconds or so out in your periphery, and we can ask you to make some judgments about the stimuli that are peripherally shown. And you might notice here that this thing is oriented kind of like that, and then over in G, it's going to be flipping its orientation by some amount, right? And yeah, right from here to, let's see, where do we get a flip? Might not be really obvious, but one of these is going to flip, and you've got to say same time or different time, and the same thing as Alex mentioned for spatial frequencies. Some of these are going to be fatter than others, okay? So it's always the same retinal stimulation, and you're making one of two kinds of judgments. Just like in the Stroupe, we're doing either semantic or sensory. Right here, we're going to be doing either spatial or temporal. Okay? Okay, there are a ton of graphs, and I don't want to overwhelm us with those, but I wonder if we can just look at some of the graphs to get a feel for what we find in the data. Okay. And a couple of folks put up some really nice draw twos here. Okay? So over here, we're plotting D prime. And this is how good you are at judging the spatial frequency differences when the two targets are landing in your left visual field. So if you're looking right over here, I'm now in your left visual field, and I have some narrow stimuli and some fatter stimuli, and you're that good at judging that difference in the left visual field and the right visual field. Okay? And we show you exactly the same stimuli, but we ask you to make some timing judgments, and we're doing that well in the left visual field and only that well in the right visual field. So there is our right visual field deficit. That's what it would look like if we're expressing it in D prime. And it is specific to the timing task. It's not a general deficit out here. Okay? It's specific just to that timing. Can you show me D prime? I asked you to draw D prime, but we'll ask you about using your hands. Okay? Let's talk about D prime in, we'll go here. Show me D prime for this one. Okay? And then show me D prime for that one. Let's do that again over here. Okay, so look how tall that D prime is. So that's a really big D prime. Okay, and then we go over to here. Okay, I think I see people doing that. Let's go back to this way. All right, and now everybody's, yeah, this is pretty cool. Okay, so we're now doing exactly the same timing over here as we have over here, but we're getting this kind of a response when it's on your left side, and we're getting that kind of response when it's on your right side. Same stimuli, one more time. We ask you to judge spatial frequency, and there are no differences on the spatial task. So there seems to be a time-specific deficit out on your right-hand side. Okay, pretty interesting. Okay. All right, that's one of the main findings. Okay, we're expecting that much. Okay. And we talked about some of the different hypotheses, and early on, what we come to the conclusion that it's really not neural noise. It's actually low temporal acuity that's driving the effect that we see there. Okay, let's see. Why don't we spend just a little bit of time on figure 8, 9, and then we'll go on and do something else. All right, so now we're doing something in the world of training. We're going to train people, and we'll look at them before training. That's shown here in brown. Okay, and we're going to look after training. Okay, and we're going to look on the spatial task and the temporal task. So let's take the spatial task just for a moment. Okay, and we can take the right visual field or the left visual field. But here we are on the right visual field, and hopefully these two look like they're about the same. They're within an error of each other. People okay with that? Okay, so even though we spent a lot of time training, we're not actually getting better on the spatial task. We're making a huge improvement on the temporal task. We're getting significantly better in the left visual field, and we're getting significantly better in the right visual field. Here again on the spatial task, we're really not getting better. So what's cool about that is we've kept retinal stimulation the same, but now we're getting an improvement that is task-specific. So this is going to be pointing to some deficit that you've got that's occurring relatively later in the visual pathway, not quite so early. Okay, okay, and then we'll try one last one. And we'll go to here. And we'll focus again just on graph A, just in the interest of time and to keep things somewhat simple. Okay, you might notice that these error bars are largely overlapping here. These error bars are largely overlapping here. We have the prior location. We also have a novel location. We're getting generalization from one tested area to another tested area. So it's almost as if what we've learned generalizes to new areas. And to put this all together, and dial all the way back, that pattern of outcomes tells us that we've got quite a bit of generalization that goes on, at least with respect to location. And so we're looking toward something like this. We're looking toward a relatively late, relatively late stage where we had the limiting factor. So it wasn't in the connection. We actually had a bad amplifier, is what's going on there. Okay? It could have been the case that it was the guitar that was throwing us off. It could have been the chord. But the pattern of activity that we get suggests to us that this had been setting the stage, had been setting the limit on the precision with which we can make these judgments. Who's okay with that? Is that working for us? Okay. That's a lot. There's a lot to think about, a lot of different ideas. And I realize it's late on a Friday, so I appreciate you bearing with me. Okay, why don't we open it up for one or two questions, and then I want to begin to make a connection to what we're going to be doing next week as we're talking about the auditory system. Okay, thanks.
So the overall findings are that there is something wrong with the amplifier.
Yeah, okay, that's a good way of putting it. So, and when we're saying something wrong, we're trying to explain this phenomena that somehow we're deficient over here, and we're pretty good over here, and that deficit seems to be located at what we would call informally the amplifier. It's happening quite late in the visual pathway. Okay? Quite late in the visual pathway. It didn't have to be that way. It could have been at a more intermediate step. It could have been at a very early step. But the fact that we're seeing this notion that we don't get transfer to novel tasks, okay? We got training that was specific to the timing task and didn't generalize to the spatial task, but it generalized everywhere on the temporal task. Didn't matter where it was. That pattern turned out to be consistent with the amplifier. I like the way that you put that. Something else. Okay. So again, maybe a bigger picture idea is behavioral brain research. We can find that we have some kind of performance deficit, and we can align our behavioral tasks in such a way that it might reveal the stage in the visual pathway where the deficit might be originating. And here we're getting a relatively late stage finding. Okay? Something else. Okay, yeah, thank you.
Can you explain like the figure 3 again and how exactly?
Sure. Okay, let's go back to figure 3. Right. Let's go back to figure 3. Thank you. Okay. So what we've done over here, we'll just start out with this much that's not in dotted line, okay? And then we'll add this extension here for figure 3. Over here, we're going to keep retinal stimulation the same, and we're going to then pull out two different tasks from that given level of retinal stimulation. So far, so good. We're kind of in the Stroupe world, okay? We're going to keep retinal stimulation the same, and we're going to ask you sometimes to report the sensory information, and then other times to generate the semantic information. Okay, so we have two different tasks operating on this bit. And the take-home message from figure 8 was that when we do practice, we get better here, but we don't get better here. So it could not have been the case that the limiting factor was down this way. Okay? So now what we need to do is take one other test. We can now change the location of the stimuli slightly. We're stimulating now a new location on the retina, and we test this one more time, and we find that we in fact do get better even in brand new locations. Okay? So it could have been the case that this was the one that was doing the trick for us. So we take that out, we keep that constant, and now we are getting better. Okay? And that's going to say that this is going to be setting the limit. Is that? Yeah. Okay. There's a lot of logic there, right? So hopefully the pictures lay it out for you. Okay, that was all about simultaneity. It's one particular feature, and if you're attending to time, you get an improvement as you're working on the test, and you don't get an improvement in space when you're attending to time. You don't get this free of charge. So there was an attentionally contingent component of this learning. If you're attending to simultaneity, you got better on that. On exactly the same stimuli, if you're attending to spatial frequency, you didn't get better. So we had this attentionally driven learning bit. Attentionally driven learning, I'll put it that way. Okay. Now that was all visual simultaneity. What I'd like to do is begin to set the stage for next week. And why don't we go to this? Okay. So what I'll ask you to do is think about this flam jam that I'm going to play. Some of you who are here over the summer might know that we have a nationally ranked drum and bugle corps. This is the drum line from the Bluecoats, who are from Ohio, and they do practice here. They come from all over the world, but they practice here. Their home base is in Canton, Ohio. And they're going to play flams. Who's heard of flams before? Okay? Madison, can you play for us a flam? No? Okay.
I was just in marching band, so I heard the...
You've heard the phrase, okay? Can somebody play for us a flam? Okay? All right, there it is. Okay, there it is, okay? So what we can have is, one more time. Ah, beautiful, okay? So his left hand hit just a little bit later than his right did. They are asynchronous, they are not simultaneous, okay? And you can have relatively extended flams or tighter flams. Can you give us some of those? Okay, that's a really wide flam, and then they can be spot on with each other, okay? Versus, okay? And so what we can do is measure how precisely people can hear that asynchrony, all right? And you can imagine that if you're a snare drummer and you're doing these exercises, you get to be really, really precise about that. So I'm going to play just a couple of minutes of Blue Coat flam jams, and you'll hear them go through their routines. And I want you to watch for when their sticks are actually hitting at the same time or hitting at different times. And then at your leisure, close your eyes for a couple of seconds, open your eyes, and see if your capacity to hear the flams is in some way facilitated by also having vision, or maybe there is no facilitation there. Okay, so we'll see if you can hear the flams versus hearing and seeing the flams. Okay? So here we go. And Alex, could we turn that down so we get a real nice contrast here? Thank you. Okay, remember, sometimes eyes open, sometimes eyes closed. That's about 2.5 minutes of flam jam, all right? So subjective observations about differences between eyes open and eyes closed. Okay, what'd you get?
It didn't work either way. Like it was just a nice sound anyway I heard it.
It's amazing that there are like 7 people playing that. I think I hear one drum. And occasionally, I'm watching them and I think I hear flams, but it sounds like, the flam is coming from that one guy, but there are 7 guys there, right, or however many there are. Some other ideas? Anybody have an observation about eyes open versus eyes closed? Okay, thanks.
I found it really hard to follow the motion of the stick, and it was almost like I wasn't really receiving much visual information at all.
Okay, so that was almost confusing. It was almost too much, okay? All right. Yeah, there's a lot going on there. And by the way, they are stationary. If you watch them on our field, and they are on that field most of the summer, right? They're sprinting when they're doing these things. These guys are in great shape. They bring in exercise physiologists, and they strap up heart rate meters to their chests. Sometimes they're up at 212 while they're performing, and they keep that up for like maybe 5 or 10 minutes. They'll be at 212. Pretty amazing. Something else about visual and okay, thanks, Jake.
Not so because you felt but those are from what I've gathered, those are really tight plans.
I was going to ask if somebody could tell us, what does it mean whenever you're hearing two musicians and this, wow, they were really tight. What does that mean?
It's hard to describe.
It's probably got something to do with simultaneity, right? Okay, right, all right. Okay, so we can have visual simultaneity, we can have auditory simultaneity, we can compare the two senses to each other and say, for example, that your visual simultaneity thresholds are relatively large, your auditory ones are tighter. Your auditory system actually is a faster system than is your visual system, as we'll be finding out. Okay, we're just about out of time. So thanks for a good session. Thanks for putting up with a very difficult article. I realize how difficult that was. It's probably the most difficult one we're going to have. Okay? All right, I will see you on Monday when we do have a TED Ed on auditory phenomena, specifically the physics of sound. See you then. We'll go out to the blue coats. All right, see you. Is there some group that's running participants today?
Yeah.
You are? Okay, I got the stuff over here.